Well, previous lesson we discussed about classes, about main concept of object-oriented programming. We discussed about terminology, what is object-oriented design, object-oriented programming. We consider some example, what is a class, the concept of class, and we consider some particular example of classes in C++. The outline of this lecture is here on this slide. Maybe we consider only the first half of the lecture, just up to this pointer, and about the pointer this we discuss on the next lesson. Let me remind you about the general form of class declaration. It looks like this. You should write a keyword class in your program. After that, you should write the name of the class. The class declaration contains two parts. The first part is hidden. It contains implementation details, hidden fields, hidden variables, hidden functions. And the second part is public. It contains open part, the fields, the functions that are open for the users of this class. When you write a declaration of the class, don't forget the last semicolon. The last semicolon after the close brace here is obligatory. On previous lesson, we considered some simple example. The example of class complex. This class corresponds to the so-called complex number. What is complex number? I show you on something happens with my browser. Okay, I start another browser. If you type complex number, the first link to the Wikipedia page, and you can read what is a complex number. In general case, complex number is represented by the pair of real numbers that called real part and imaginary part, re and im. And in this declaration, I exactly follow the definition of the complex number. I declare the two data fields, two members of this class, re and im. These members are private and public functions. Let me copy this part of the code into the Visual Studio. Well, I comment these two functions. I implemented a little bit later. Now our program contains declaration of a class complex that contains two functions for getting and setting the real part the member field re, and two functions for getting and setting imaginary path im. Let's implement the function print that prints number to the screen. To show you this process in details, I implement this function outside of the declaration of the class. In this case, we should repeat the class name. After that, put here 4 points and the name of the method that we are going to implement, print. This method is very simple. Let's print the real and imaginary part to the screen, but let's print it in this form. The first, let's output real part. Next, let's output imaginary part of the real number, of the complex number. And let's enclose this in brackets. The keyword const that is written after the declaration of the method print tells to the compiler that this method doesn't modify any data members in this class. If I try to compile this program, I see the message succeeded. But in the case, if I try to modify the data members, compiler shows me the mistake that I cannot modify the data memory. This is due to that this method is declared as a const. If I remove this keyword, modification of the data members will be permitted. But of course, if the method just prints the data members to the screen, it's better to declare this method as a constant. Well, if we have such declarations of the methods, now I can declare particular instances of the class complex that are called objects. In the main part of the program. Now the variables x and y are the variables of the class complex. As far as re and im are closed fields, I cannot get access to these members. If I put x point re, compiler outputs me mistake that the member field re is inaccessible. To modify it, I can call the method set re and specify their particular value of the real part of the number x, and set im for stating the imaginary part of the complex number x. After I set this number, I can print the number x to the screen. Let's put here end of line. And now we can check this program. We will see the complex number with real part equals to 0, imaginary part equals to 1. Well, let's come back to the presentation. Well, I show you how to declare an object in a program, but let's consider it in details. And first of all, a few words about terminology. The class, the word class more or less corresponds to the word data type. And if I said that I declare a class, it means that I declare a new data type. But when I said that I create an object, it means that I create a particular variable of the corresponding data type. There are two ways to create an object. I can create it statically. To do it, I should write a class name and object, and after that, object name. Object name is just an identifier that I should write according to the rules of creating identifiers in C++. But in some cases, it's better to create this object dynamically. This is a general form of the declaration of the object using dynamic memory and operator of allocating the dynamic memory new. And this is how it looks for the class complex. This line I already show you in Visual Studio. Yeah. I declare two variables of the type complex x and y statically. But now let's create an object dynamically. Let's declare a pointer p of the type complex, and let's assign to this pointer the pointer to the memory allocated by the operator new. After that, p will be the pointer to the class, to the object of the type complex. How to work with object using pointers, we consider just a few minutes later. First, how to work with the objects created statically. To get access to their member functions, I can use operator point. If I declare a variable a, I can write a point set re with the parameter a point set im, a point print, and so on. On this way, I can get access to the public members declared in the class complex. Private members are not accessible. Okay, let's do it again for the variable y. Let's assign, for example, 2 as a real number of the variable y point set im 4 as imaginary part of the variable y, and y point print. Let's print the number to the screen. Set im, what happens? Or, of course, not get im, but set im. Now I declare two complex numbers, x and y, with values 0, 1, 2, 4. But how to work with the complex numbers created dynamically with pointers? To get access to the public members of the class, I can use special operator arrow like this. Pointer, arrow, and the member field. Let's assign something to the object using pointer. P arrow set 3 P arrow set im 4 and P arrow print. Well, now I declare two objects statically and one object I created dynamically. And the pointer P points to this object. Let's check. Yes, we will see on the screen the message. We will see on the screen the values of the real and imaginary parts for all of these complex numbers. Well, but let's consider some details about how it works. Suppose that I created two variables of the type complex, a and b. After the declaration in computer memory, RAM means random access memory, two particular instances of the objects of the class complex will be created. The object A with its real and imaginary part, and the object B with its real and imaginary part. The data members are different for different objects. For example, 1 for real part A, 2 for imaginary part, 2 for real part B, 3 for imaginary part B. But the implementation of the methods is common for all the objects. And I call the functions set_re, set_im for different objects A and B. So to assign 1 to A, I should write A point set_re. To assign 2 for B, I should write B point set_re. But the implementation of the method set_re doesn't contain any pointer or reference to the object A or B. So how the method knows that it called from their particular object, say A or B or any other object? How it works? It works due to the so-called this pointer. The answer to this question is as follows. Every member function is called for some particular object. And every member function has one latent parameter, the pointer to the object which calls it. And this pointer, the pointer is accessible as this. Again, let me repeat, this is a keyword, and it means the pointer to the object that called particular function. When I call the function set_re for the object A, the function set_re gets the pointer this to the object A. When I call the function set_re for the object B, the function set_re gets the pointer this to the object B, and so on. So this pointer points to the particular object that called this function. On this slide, you may see two different implementations of the method set_re, but these implementations are identically equals. Re equals to underline re, and this arrow re equals to underline re. Two different implementations are identically equals. Let's look again to this picture. Again, imagine that I create two objects A and B. It means that in the computer memory, it will be allocated two double numbers for real and imaginary parts of the object A, and two double variables for real and imaginary part for the object B. But when I call these functions, A point set_re and B point set_re, this function gets this hidden parameter, the pointer to the object that called it, this. And in the first case, this points to A, and in the second case, this points to B. Let me show you this in Visual Studio. Let's come back to the implementation. For example, what function set_im, set_re, but it doesn't matter, of course. The implementation is written here. The program is correct if I these semicolons are not necessary, I can remove it. The program is correct, but it still be correct if I type here the pointer this. As you can see, the word this is shown with a blue color. It means that this is a keyword. You cannot create a variable with the name this. You cannot create a function with the name this. You can use the word this only in a predefined sense as a pointer to the object that called the member function. Let's compile the program, and you can see that the program still be correct. There is a simple rule when we should write this. In simple cases, it can be omitted. Like in this case, re equals to underline re. When there is no conflicts, you can omit the keyword this for simplicity of the program. But in some cases, I can show you. Suppose that I pass the parameter to the function with the same name, re. Now it will be conflict of the names because this parameter has a name re and this data member has a name re too. And this assignment doesn't modify the data field of the class. It modifies only the temporary variable, temporary parameter re. If I try to run this program, I will see that the real part of the complex numbers are undefined. I can see undefined value here as a real part. Again, because there is a conflict of the names. The name of the parameter has the same name as a data member. To avoid this mistake, of course, it's better to write different name for the parameter. But suppose I have the same names. In this case, I can use this. If I write this arrow re, it will be the data member, not this parameter. Yeah, you see the correct result. You see the correct result on the screen. But of course, it's better to give the different names for the parameters of the methods and the data members of the class. When I give different names, I'm sure that it will be no conflicts of the names and the assignment will work correctly. Well, let's consider one more case when the pointer this can be used. Suppose that I want to implement the function append that will work similar to the operator plus equals. In this case, due to the according to the syntax of C++, I should return the new modified class, and I should return the pointer this with a star. It means that this function will return this object. And let me show you this example in Visual Studio. The method append that appends to numbers. By the way, let's implement this method as a standalone function. Let me write the implementation of the method outside of the class. In this case, I should repeat the class name before the name of the function. In our examples, all of the functions are not very large. And it can be implemented inside of the class, but I show you this implementation outside of the class just as example. Now, the function append returns the new value of the modified class, of this class that is modified. Let's check. Let me declare the third object z, xyz, and let's assign z x point append y. And after that, let's print x and y again. X, y, and z. Let's print, let's output here the message that these values are after the operation. After the operation append. What will we see on the screen? We will see on the screen the previous value of y, new value of x, and new value of z. The first value of x and y will be 0, 1, 2, 4. New value of x will be 2, 5. I add these two numbers. Old value of y is 2 and 4. It still be 2, 4, and the value of the object z will be 2 and 5. Well, this is some features of the declaration of the functions. Maybe in the end of this lecture, I will show you the implementation of the one more method. The method append, it works like plus equals operator. But let's implement the method that works like plus operator. Let's call it add. In this case, the method add should return a new value of the result without changing the values of the object that took part in this operation. Add. In this case, I should declare new variable of the type complex as a result. The real part of the result will equals to real part plus c point real. The imaginary part of the result equals to imaginary part c point in, and we should return the result. As you see, the current object, the values of the data members of the current object are not changed. Now let's output the values of x, y, and z after the operation add. What is the difference? The difference is that we will see the old values of x and y and new value of z. Well, this is a declaration of a class complex. This class is more or less simple, but even in this simple case, the implementation of the method can take a lot of lines of the code, and the source file can be very large. In this case, the declaration can be separated to the different classes, to the different files. Let's do it. Let me add a new header file. Let's give the name complex to this header file. Okay. And let's add a new CPP file. Let's give the same name complex to this CPP file. And after that, I can move the declaration of the class into the H file and the definition of the members. Definition of the members to the C++ file. As you see, compiler doesn't know what is complex. Let's write include complex point H. Compiler doesn't know what is cout. It's not a problem. Let's write include IOStream and using namespace std. And here in the main part of the program, compiler don't know what is complex. Again, to do it, I should write include complex.h. Pay attention that for user-defined header files, you should write oops. Okay. Let me store. Well, for user-defined header files, you should write include in double quotes. And for standard header files, you should use another type of brackets. This one. Different type of brackets, different type of quotas for user-defined header files and the standard header files. Now, you see that our program becomes significantly shorter. I divide my program into three parts. The main part, the declarative part, where I declare the class complex, and the file that contains a definition of the methods from the class complex. And it works. It works. If I compile this program, I will see the message. Okay, the program is succeeded. Well, on this way, we can write rather large classes, rather large programs, divide it into several files, and compile it in one solution. Let's check again that this program is correct. Yes, it works. Well, that's all that I want to show you today. Let me stop recording.